Let's look at the confidence interval for the mean when the standard deviation sigma is known. This argument is pretty complicated, but I think it's worth presenting, so I hope you can follow it. If a variable is normally distributed, then there is a 95% chance that its value is within 2 standard deviations of the mean. What variable are we going to apply this to? Let's apply this to the variable x bar. The sample mean x bar is normally distributed if either x is normally distributed or the sample size n is large enough, say n is greater than or equal to 30. In either case, if x has mean mu and standard deviation sigma, then x bar is normally distributed with mean mu and standard deviation sigma over square root n. Again, there's a 95% chance that mu is within 2 standard deviations of x bar. Really, it's 1.96 standard deviation. So again, there's a 95% chance that mu is within 1.96 standard deviations of x bar. Another way to put this is that the probability that mu is between x bar minus 1.96 sigma over square root n and x bar plus 1.96 sigma over square root n, the probability that's between those two is 0.95. Sigma over square root n is the standard deviation of x bar. The interval from x bar minus 1.96 sigma over square root n to x bar plus 1.96 sigma over square root n is a 95% confidence interval for mu. There is a 95% chance that the actual value of mu is in this interval. If we take samples and use them to construct confidence intervals over and over again, then 95% of the confidence intervals will contain the population mean mu. That's why we call it a 95% confidence interval. We are 95% confident that mu is going to be in that interval. So again, the interval from x bar minus 1.96 sigma over square root n to x bar plus 1.96 sigma over square root n is a 95% confidence interval for mu. The endpoints of this 95% confidence interval are x bar plus or minus 1.96 sigma over square root n. Let's look at an example. A study of 66,831 dairy cows, yes, these are real data, found that the mean milk yield was, what do you think? What do you think the average dairy cow produces per milking? How much milk? Turns out it's 12.5 kilograms, which is about 3 gallons, or roughly 12 liters. Assume the standard deviation is 4.3 kilograms per milking. Construct a 95% confidence interval for the average milk yield in the population. Now, we've seen before the endpoints of this 95% confidence interval are x bar plus or minus 1.96 sigma over square root n. We were not told that the milking is normally distributed, but because the sample size is so large, we know that the distribution of x bar is going to be roughly normal. So the endpoints are x bar plus or minus 1.96 sigma over square root n. X bar in this case was 12.5. That was the sample mean. Sigma, we were told, was 4.3 kilograms per milking. That's the standard deviation. And the square root of n, square root of the sample size, that's the square root of 66,831. So those are the endpoints of our 95% confidence interval. If you grind it out, you find that the interval from 12.467 to 12.533 is a 95% confidence interval for mu. That's what you get if you grind out these calculations here. Construct a 90% confidence interval for the average milk yield in the population. Okay? Earlier, we calculated a 95% confidence interval. We were 95% certain that mu was somewhere in this interval. 90% is going to be a little smaller, so we're only going to be 90% confident that mu is in this interval. So the 90% confidence interval will be a little smaller. Here's what it's going to look like. 90% confidence interval. In general, the endpoints of a two-sided confidence interval for mu would be x bar plus or minus z sub alpha over 2 sigma sub x over square root n, where z sub alpha over 2 can be found in this chart. So when we have a 95% confidence interval, z sub alpha over 2 is 1.96. That's what we had in the previous example. Now that we have a 90% confidence interval, z sub alpha over 2 is going to be 1.645. So instead of 1.96, we're going to write 1.645 for z sub alpha over 2. We're talking about a two-sided confidence interval because the confidence interval will run from here to here. So it's not going to be open-ended. It's not going to go to infinity in either direction. Instead, it's between this finite value and this finite value. And that's why we call it two-sided. So again, here are the formulas we're going to use. X bar plus or minus z sub alpha over 2, sigma sub x over square root n, where this is our z sub alpha over 2. Z sub alpha over 2, what do we mean by that? Okay, so we have a 90% confidence interval. This area over here is 0.9. Another way to put this is that the confidence level is 0.9. So the probability that mu is actually in this interval is 0.9. So if we have a confidence interval for the mean, 90% confidence interval, we want to find the z-score that corresponds to this value, okay, the boundary of the 90% confidence interval. So if this is 90%, what do these two areas out here add up to? Well, that's going to add up to 0.1 because the whole area has to be 1. So if this area is 0.9, then this stuff over here and this stuff over here, they have to add up to 0.1. Another way to put this is that our level of significance, alpha, equals 0.1. It's just the area to the left and the area to the right of the confidence interval. So if the whole area is 0.1, what is this area? What is this area? Well, you can do the math. Each of those is going to be 0.05. In other words, if the whole area is alpha, then half of the area is 0.05. That's going to be alpha over 2. And that's why we call this z sub alpha over 2, z sub 0.05. Okay, it's a complicated argument. We call this z sub 0.05 because the area to the right of it is 0.05. That's why we call it z sub 0.05. Okay, so again, in this case, we want a 90% confidence interval, a level of significance 0.1. So our critical value, z sub 0.05, is 1.645. That's the z value, the z-score that corresponds to this. Okay, so here's where those numbers come from. We could just get those from the normal chart. The endpoints of a 90% confidence interval are going to be x bar plus or minus 1.645 sigma sub x over square root n. In other words, x bar 12.5, 1.645 because it's a 95% confidence interval. The standard deviation of x is again 4.3, and square root of n is square root of 66,831. So when you grind it out, you find that a 90% confidence interval is 12.473 to 12.527. Notice it's going to be a little bit shorter, a little bit smaller than the previous interval we saw, the 95% confidence interval. What do we mean when we say that this is a 90% confidence interval for mu? There is a 90% chance that the actual value of mu is in the interval from 12.473 to 12.527. Not a 100% chance, but a 90% chance. Good chance. Find a 92% confidence interval for the population mean mu. To be honest, we usually work with 90, 99, 95. 92 is not very common. But if we did come across a 92% confidence interval, here's how we'd calculate it. Okay, 92% confidence interval is going to look like this. So the level of significance in this case, gosh, what do those add up to? Well, level of significance is going to be 0.08. Alpha equals 0.08, which means that alpha over 2 is 0.04. So this area here is 0.04. So we need to find z sub 0.04. We need to find the z-score that corresponds to this value. So that the area to the right is alpha over 2, 0.04. Okay, so if x is normally distributed with mean mu equals 0 and standard deviation 1, there's a way that we can find it. On the TI-83 under distur, inverse norm of c tells us the value of x such that the area to the left is c. So in this case, z sub 0.04, if the area to the right is 0.04, that means the area to the left is 0.96. So what we would enter is inverse norm of 0.96. That's going to tell us the z-score such that the area to the left is 0.96, and thus the area to the right is 0.04. And we get 1.751. Okay, so the endpoints of a two-sided confidence interval for mu, we've seen this before. X bar plus or minus z sub alpha over 2 sigma sub x over square root n. So the endpoints of a 92% confidence interval, those are going to be x bar plus or minus 1.751 sigma sub x over squared n, because z sub alpha over 2, that's 1.751. Plug in the numbers we've seen before, we get this. 12.5 plus or minus 1.751 times 4.3 over the square root of 66,831. Grind it out, and you find that a 92% confidence interval is going to be 12.471 to 12.529.